All right, everyone, so today we're going to go over induction. Now, in induction, there's three steps. First is identifying what is the base case, what is the minimum value, the smallest value, the minimum possible case for which the thing that we're trying to prove exists and holds true. So that's the first step. Next step is what is the inductive hypothesis? This is typically an assumption that you make where you assume that something is true, and then you want to prove that this also is true for XYZ. And then the third step is sort of bringing that together and proving that if it works for this, then it also works for this, something of that nature. And so we have, in this case, we want to show that the sum of the first n integers is n times n plus 1 over 2. We have our base case, which, as I mentioned before, is the minimum possible value for which that formula or what we're trying to prove holds true. So in this case, it's 1. And obviously, this formula holds true for 1. And our inductive hypothesis is we're going to assume that for integers 1 to k, that this formula holds true. So for integers 1 plus 2 all the way to k is going to equal k times k plus 1 over 2. That's our inductive hypothesis. We're going to assume that that is true. Then we want to prove that if it works for uh, uh, if it works for n equals k plus 1, we want to show that the sum of all integers up to k plus 1 equals k plus 1 times k plus 2 over 2. So we want to show that if it works for one integer, for one any k, we also want to show that it works for the integer following k. So k plus 1, we want to show that. And so we can break this down by saying that the sum to the first k integers, k plus 1 integers, is equal to the sum to the first k integers plus the k plus 1. So we want to show that the summation of that equals to k plus 1 times k plus 2 over 2. And so if we do that, then what we'll show is that if this formula works for n equals k, then it also works for n equals k plus 1. And so here we show, right, because we have assumed that it works for n equals k, right? And we want to show that if it works for n equals k, it also works for k plus 1. That's the inductive step that we want to show. We have our inductive hypothesis. We're using that inductive hypothesis to show that the summation to the next integer also holds true. The formula also holds true for that. And so we're showing that if it works for n equals k, also works for n equals k plus 1. So we can break this down. And then we're able to show that the sum of the first k plus 1 integers is equal to the sum of the first k integers plus k plus 1 through this obviously algebraic simplification. And then we have shown that it does equal to one another. And this is what we wanted to prove for n equals k plus 1. And so it works for k. It also works for k plus 1. So now we have two things that we've shown. We've shown that it works for the base case. It works for n equals 1. And we have shown that if it works for any integer k, it also works for any integer k plus 1. Right? From our inductive hypothesis, we've assumed that if it works for k, and we have proved that if it works for k, it also works for k plus 1. Well, then, because we've shown that and the base case, right, we can simply extend out the base case. So if it holds true for 1, we know it holds true for 2. Then we know it holds true for 3, 4, and so on. And so this is what we wanted to prove. Since it holds true for n equals 1, and since we have shown that it holds true for n equals k, it must also hold true for n equals k plus 1. That's the inductive step that we've shown. And so that through this principle of mathematical induction, we have shown that the summation of the first n integers equals n times n plus 1 over 2. So that's induction in a nutshell. And I guess we want to break this down further. Like what obviously we know we need to have a base case. We need to have an inductive hypothesis. We need to sort of bring those two things together. And we also want to, one of the main things is what do we want to prove? In this case, we wanted to prove that if it holds true for k, also holds true for k plus 1. So when dealing with induction, you want to think about, okay, what's the next thing that we want to prove to show what's the inductive step, right? What's the inductive step that's going to go on, and that's going to show that our statement holds true for like all integers or whatever the statement is. And so typically it's like the next one we want to show it holds true for this version, also holds true for the subsequent version as well. So it's typically that, but we really want to show what's the inductive step here. We look at gradient. Okay, that's going back to the notion of slope and gradient. So obviously in 2 dimensions we have derivatives, we have instantaneous rate of change. So the entire purpose of a derivative means that it's the instantaneous rate of change. We look at a slope of the derivative of x squared or 2x, right? It's at any point the instantaneous rate of change we can get by using 2x. And similar concept here for gradient, but in 3 dimensions we have the notion of direction of the greatest initial increase. So when you think about gradient descent and like how all these like optimization algorithms or machine learning work, they want to minimize a loss function. How do we minimize a loss function? One of the ways that we can do that is through gradient descent. And the reason that gradient descent works is because by definition, gradient is the direction of the greatest initial increase. If we take the opposite of that, then that's the direction of greatest initial decrease. And so that's why gradient descent is used in a lot of optimization problems when we're minimizing the loss function. So if we're taking the gradient of, let's say, f of x1 to xn, that is just the partials of all of the terms divided by respect to that variable. So just an example, if we have f of x, y equals x squared plus y squared, it's a derivative of f with respect to x, comma derivative of f with respect to y, so 2x, 2y. And however many variables you have, you would take the derivative with respect to that variable. So what does this mean? So if we have our x squared plus y squared, right, 3-dimensional graph, this means that the direction of greatest initial increase is that 2x to y vector, right? That 2x to y vector, if you go in that direction, you will go in the direction of greatest initial increase. Now, if you go in the opposite direction, you will go in the direction of greatest initial decrease. Okay? And so sometimes, even if you do follow the direction of greatest initial decrease, you might not actually get to the global minimum. And because we're going in greatest initial increase, it might be the case that we want to take a slightly lower initial decrease, such that later on we actually get to a global minimum. Right, so it's possible that the direction of greatest initial decrease, doing that continuously, might not actually get you to the global minimum. So that's another thing to note. It's a common thing we use in machine learning of gradient descent. Let's talk about valid number palindrome. It's a pretty simple LeetCode question. And I think one of the things we can learn from this LeetCode question is identifying the types of information that you need first in order to solve the problem. So you don't just go into and solving the problem holistically, but okay, like thinking about, okay, what are some pieces that I need to know first? So in this case, we need to know the length, but we'll go into that. So the entire question is we have a number, let's say 246. We want to see if this is a valid palindrome. So if we reverse this integer, does it equal to itself? And if it's negative, that is not a valid palindrome. So if it's negative, we automatically return that's false. So if it's 246, how can we determine that it's a valid palindrome? So the first step is to determine the length or the number of digits within the number. So how can we get that? So if we have 246, we can divide by 10, count the number of times that we can divide by 10 before we get to a number that's less than 1. Okay, so if we get to a number that's less than 1, then we know that's the most amount of times we can divide this number by 10, and not get something that's less than or equal to 1. And so this actually helps us get us the lengths, because if you look at 246, right, then we're at 24.6 or 24, then we're at 2, then we're at 0.246, right? So we can do this. We can divide 246 2 times, right? So it would be 24.6. So it would be 2.46. And then after that would be 0.246. We can divide it 2 times before we get to a number that's less than or equal to, that's less than 1. So the ideal number, it would be 3, right? That's the number of digits, right? But in this case, when we do a reverse, we actually want, because this is 100, this is 10 squared, we want 1 minus that. So 3 minus 1, right? That we want 1 minus them. That's why we do the I equals I minus 1 here. Okay. And now, so 246, right? We've gotten the number of digits, subtracted that by 1. Why did we subtract that by 1? Because we want to, the first digit, if you reverse the ones, that's going to be a 600. Or it's in the hundreds, right? So we need 10 squared, right? We would need that 2 instead of the 3. So that's why we're subtracting by 1. And so we have 246. And we know, right, we're starting off 2 with 2. I equals 2, 10 squared, 100. So now we take, one of the things you can do is we want to get, for the first step here, is we want to get the last digit. We want to make it the first digit. So how do we take the last digit? We just mod 10. That's how we get the last digit. That's our last digit is 6. Now we can multiply that 6 by 10 squared, and again, the squared comes from our length calculation, the length minus 1 calculation. We can multiply it by 10 raised to that calculation, and we get 6 times 10 squared, we get 600. We can then update our 246 number to get rid of the 6. And now how can we do that? Well, we subtract the 246 mod 10, which is 6. So subtract the 6, that's 240, right? And then we can just divide by 10, and that will give us a 24. That essentially that removes the last digit. And so now we do the same process again. So 24 mod 10, that equals 4. 4 times we decrement our I by 1, so it's 4 times 10 times to the 1. That's 40. We add the 600, we add the 40, we get 640, and then we do the same thing for the last digit of 6. And then we're able to get, or for the last digit of 2, and then we're able, so right, we have 24. We get rid of the 4, 20 divided by 10, we get 2, and that's all. And we do 2 times 10 to the 0, right? So that would just be 2. We add that onto our original number so that we get 642. So that's how we reverse, as we just went through an example. That's how you would reverse an integer. So we get from 246 to 642, and then you can just check if these are equal, and then you would return if it's a valid palindrome or not. So this is a pretty standard, simple question, but you can learn many different things from it. So first is starting off with an example. The fact that we started off with an example of 246, how can we, if we weren't even doing this through code, if we're just trying to reverse this number, how would we go about doing it? Using an example and then translating it to code. We can see the importance of that. We can see the importance of what information we may need first. So as we were mentioning before, we would like to know the length minus 1, right? We would like to know up to what power of 10 does this number represent? We're 10 squared, right? Hundreds. And from that, we would need to know the length. So what information do we need first? We can learn from that. Solving an easier version of the problem is another just standard standard technique that you can use. What's an easier version of the problem? If the problem itself is too difficult, first, can I solve an easier version of it? And then how can I extend that solution to be able to solve this general problem that I have? And then you can learn a lot from just one example. One of the common things is that you may be tempted to just do many different examples, but there's a lot of nuance and learnings that you can make just from one problem. And so you really want to take advantage of that. And just a couple of different things. So first is in terms of cultivating work into play. So first is a sense of ownership over the work that you're doing. So right, going back to a lot of previous mentalities that you might have had. What are points in time where you really felt a sense of ownership, a sense of power over the work? And really getting back to that. How can you cultivate an attitude or a mindset where you're able to get back to those instances or previous points where you were able to have that sense of ownership? And there's 3 P's if you want to cultivate this sense of energy in your work, which is power playing people. This sort of gets at the power part of it, like how can you have more ownership, which is associated with having more power. So power playing people. And then another sort of tactic is we'll go to, I guess, sort of this concept of play, so power play in people. So there's this book called Actionable Gamification, and what it talks about is what makes video games addicting, what makes like the nature of games so addicting, and we're able to apply it to different parts of our life. So how can you convert something that's seemingly boring, seemingly mundane? How can you make it more fun? You can turn it into a game, which we refer to as gamification. There's different tactics in that book. One of which is just having a scoreboard, so or like a number of points scored, or any way to convert something that you're doing into a number, and that's a way to make it more fun. And finding a way to add additional layers to make the work that you're doing more fun and enjoyable. So this is obviously going above and beyond what is natural, what is naturally asked of you will help you bring that energy in all aspects. Because when you're able to add something that you're not directly told to add or told to do, it gives a sense of power, gives a sense of play, gives a sense of energy, also sort of stretches your creative energy in many different ways, and you're able to have a sense of ownership over what you're doing. And three is coming from a place of boredom, right? So you're just doing something not because you have to do something, but because you're coming from this different place mentally, and then you're doing the craft. So that's another sort of like perspective to have. And so how can we become more creative with the project or task that we are given? So part of this is we're given some sort of task, we're given some sort of project. What are the different creative elements that we can use to make this project even better? Right? How can we, and it doesn't even have to be better in the context of others' expectations. Like, how can you just add things you've learned, or just like stats or data science, depending on the field, right? Stats, data science, anything you've learned, how can you make it more creative? How can you just add something new to it, add something, um, add like a natural part of what you want to this entire project or task, and that will make it more energizing. And how are we able to incorporate, right, other parts of CS, stats, data science, again, depending on the field that you're in? How can we incorporate even PCA and being like as even if it's like a long stretch connection, just incorporating that will help you sort of stretch and build more creative energy in your mind. So right, stretching those creative muscles, right, absolutely essential and pivotal, making things more fun, more challenging, and the repetition will help out with the mental adaptability, right? So your mental state will naturally adapt to the environment that you place it into, and so with you're able to when you're able to stretch these creative muscles, when you're able to be more creative, add more creative parts to any single task or project, you're able to sort of gain additional energy, and it makes you more motivated to do that moving forward. Also, just having a meta awareness of nature and what to expect, and sort of even using like different parts of examinations or other tasks that you've seen to like cognitively reframe how you view certain things. That's also essential. And then now let's just talk about the Fibonacci sequence. So the Fibonacci sequence is a very popular sequence. We're starting with 0, 1, 1, 1, 2, 3, 5, 8, and the next subsequent number is the sum of the previous two numbers. So this calculation of this falls into a nice tree diagram. So if we want to calculate fib of 6, we have to calculate fib of 5 and fib of 4. To calculate fib of 5, we need to calculate fib of 3, and fib of 4. To calculate fib of 4, we need to calculate fib of 3, fib of 2. Now, if we were to do this for, let's say, the sixth to find the 60th Fibonacci number, computationally, it's going to be a lot, not going to be very efficient, because you can think we're in just calculating Fibonacci of 6, we're calculating Fibonacci of 4, we're calculating the fourth Fibonacci number, what, like just twice, right? So we're making this entire tree, like you can see, like this is a subtree, right? We can see these exact two trees. We're recalculating two completely exactly the same trees. So how can we make this better? How can we store the values of these? So we can just store the value of f of 4, right? When we calculate it, and then whenever we have to recalculate it, we can just bring it back, right? We have that stored in memory, and we can bring it back instead of having to recalculate it. It's going to increase computational complexity and reduce efficiency. And so this is one of the techniques that we call, which is memoization. And the Fibonacci sequence is like a perfect example. It's storing these intermediate results such that our algorithm doesn't need to recalculate or recompute um, unnecessary computations. So in this case, we don't want to recompute, right? If we've already calculated f of 4, we don't want to recalculate f of 4. We've already calculated f of 3, we don't want to recalculate that. It's just minimizing the number of only doing the necessary calculations and computations, or minimizing the number of unnecessary computations that we have to make. And so this is an important step if we want to consider efficiency in the algorithms. So that's all. So we talked about induction, talked about the steps of induction. Again, this is a very simple example, very basic example. Talked about like a review of gradient. We talked about valid number palindrome. We talked about what the things that we can learn from that. We went through how to the code behind it, how it actually works. Talked about some ways to actionable gamification, ways to incorporate play into the work, ways to make things more fun, to express your creative energy. And then we talked about Fibonacci sequence and memoization and really increasing the efficiency of these algorithms and one way to do that is through memoization. So that's it. See you in the next video.